Okay, let me start by thanking you, the audience, for staying to the end, and thank the organizers for giving me the honor of presenting this final talk at ICAP, which has been a great meeting. So I'm going to talk to you today about collective light-matter interactions. And we heard a beautiful talk this morning from Derek Chang on a similar theme, talking about the theory of 1D collective light-atom interactions. And I'm going to extend that, and many of the take-home messages will be similar, but the biggest take-home message of all is that collectively the system becomes richer, but also we can do more. And if we engineer these collective systems, we can do all sorts of things with light-matter interactions that we sort of dream of, but we didn't know how to do before. So in particular, I'm going to focus on our recent experiment, which is a very simple experiment. We just send light through an ensemble of cold atoms, and it's the experiment of Theodora and Nick, who are the current PhD students who are both here. And actually, the result to us was a big surprise, and we wouldn't have been able to, we thought there was a mistake maybe, until we had the theory of Rob Bettles, who was also here, that explained that indeed we were seeing the right thing. But the results are a little bit counterintuitive, so I hope you learn something new. And these are our other collaborators and our funding sources. Okay, so I'm going to begin by taking you right back to very basic undergraduate physics, where we all learn about resonance. And what we know about resonance is that the line width of the resonance is equal to the decay rate. And this shows an atomic system example where for atoms the line width is the natural width and the decay rate is the spontaneous emission rate. So this is something that we're all very familiar with. But what's really shocking of our experiment is that when we measure decay rate and line width, we don't see this. So we see that line width isn't equal to decay rate. So I'm going to explain to you in this talk how this can be the case, even for a very simple case where we have an ensemble of closed two-level atoms. And this was a big surprise to us. Okay, so let's start talking about these collective systems. So the secret ingredient that means that our intuition doesn't work is this collectivity or cooperativity. And what we see here is it's more than the sum of the parts. So our bulk response of our medium is not just given by n times the individual atom response. So often we associate a polarizability with atoms and a susceptibility with the bulk. And we can't just write that the susceptibility is n times alpha. Okay, and we could also use the word cooperative to describe this type of process. So we tend to use cooperative and collective interchangeably. And I'm just going to digress a little bit for my own amusement and to give a historical political message here. So I'm from this is the UK here. Well, it's actually England without Wales. And this is my hometown of Rochdale in the northwest. Durham is up here in the northeast, so I haven't gone very far in all the years. But Rochdale has a very bad reputation in Britain. Basically, if something bad happens, it usually happens in Rochdale. And the last good thing to happen was in about 1844, when these guys sat down and they formed the Rochdale Cooperative Society. So they figured out that by pooling their expertise, so to speak, they could do more than the sum of the parts. And when I grew up here, I always found it very strange that people came from Japan to this terrible town in Rochdale where I lived in order to visit this original cooperative shop that's still there, actually, and you can visit. Okay, so cooperative or collective means more than the sum of the parts. So by working together, we can do more. And we have to keep remembering this sometimes. Okay, so that's the political message over. So now let's come back to the physics. So collective light-matter interactions then. So we have a collection of atoms. And it can very quickly get very complicated. So basically, we get into this system of many photons, many atoms, and then we have, if it's in free space, we have all these modes. So this was the point that Derek made very nicely before. We have a continuum of spatial modes, which makes the physics extremely difficult. And usually this is thrown away. All this wave interference physics is thrown away. But we're going to bring this back in because it's useful to us and it helps us to understand. So I've divided this into a sort of traffic light system, where this is like sort of what we know at the moment in the green zone, where we have all of classical optics, we have all of nonlinear classical optics, continuous media, the mean field Maxwell equations that we all learn about. Then we also have quantum optics, which is relatively simple in this, still relatively simple in that we have a few photons, we have discrete systems and a few modes, usually just one spatial mode that we can get rid of. But now, if we start to add more modes, more spatial modes, and also we allow for these discrete dipoles to interact with one another, so we have weakly interacting dipolar systems that are interacting with a continuum of spatial modes, then we get into a much more complicated and rich region, which we'll call the amber region. And that's basically the interesting region where we're currently working now. And then down here, there's a kind of red zone. And this is really beyond the scope of what we currently can do. So this is kind of many photons, many atoms, continuum of spatial modes. And we're really in a fully strongly interacting quantum many sort of emergence regime here where we can't do the theory yet. So the interesting thing is at this interface where we can do experiments, and the experiments can provide us with a kind of benchmarking for what kind of approximations we can make for theory. And so this is the place where sort of I like to work, and other groups are also working, and there's interesting developments going on. So what's the tuning parameter that takes us from this sort of green zone where everything is well behaved and understood down to the red zone where we can do nothing? Well, it's basically the strength of the dipole-dipole interaction. So this is my sort of interesting tuning parameter that I want to increase the interactions between the particles. And there are many ways we can do that, and we can control that. So one is just the density of the medium. The other is the type of dipole, so we can go to Rydberg systems that have enormous dipoles. And that's really the direction that we came from. So we sort of found ourselves in this red zone many years ago, and then we had to sort of take a step back and try and sort of work out what was going on. So if we look at Rydberg systems, we have these very nice Rydberg series where basically as you step up in principal quantum number, the dipoles get bigger as n squared, and you can make these dipole-dipole interactions as strong as you want. And we've seen at this conference many nice Rydberg talks where these Rydberg atoms are now proving to be really useful for things like quantum simulation. We're also, with colleagues in Durham, we're also working on doing imaging of terahertz fields with Rydberg atoms. So this is a really practical thing where it actually looks like something that people might even want to sort of buy or use. The other thing I like about Rydberg systems is kind of generic. So you can see them, of course, in cold gases, but you can see them in hot gases, which is what's going on here. And they've got a hot gas doing this imaging. And now also we've got a new type of Rydberg system based on excitons. So this is excitons in cuprous oxide. And again, you've got these Rydberg series. So these are kind of extremes of hot gases, cold solids. And of course, we've got the more familiar ultra-cold gases that many people work on. So basically, in all our systems, we've got this ability to sort of tune the strength of the dipole-dipole interaction, which is a very useful feature in terms of like trying to control and manipulate light-matter interactions. So one of the things that has been a focus in my group has been trying to use the interaction between Rydberg atoms and going into this red zone, and then to use that for quantum nonlinear optics. So this was an experiment that we did just last year where we had basically two spatial channels, and we send in photons here and photons there. And when the photons go into the medium, we couple them to a Rydberg state, so we can map the strong interactions between Rydberg atoms onto the photon, and it imprints a phase pattern. So the dipole-dipole interaction between the Rydbergs changes the phase of the propagating photon. And that basically, this phase shift then causes the photon to deflect. So if there's a photon in this channel, then that one gets deflected and this one gets deflected. But if there's only a photon in one channel, then they don't get deflected. So it's a completely contactless, and these two channels are separated by about 10 microns. So it's really microscopic distance scales over which I can control one photon with another photon, even though they don't touch one another. So really our question that we've been asking for many years is, how do I make this more efficient so that it works basically every time? Every time I have a photon here, I deflect the photon here. And ideally, I'd like to deflect it into a particular spatial mode with some high fidelity so that I make something like a photon switch, single photon switch, or a photonic gate. So that's the kind of physics that we've been looking at, that then we came up against these sort of collective issues. And we wanted to ask, can we use this collectivity, sort of doing more using collective or cooperative effects in order to make this work better? Because our limitation, as we heard in Derek's talk, is really optical depth. Because when I send in a photon here, it's very hard to localize it in a small volume and get it to have a large interaction. So the process is rather inefficient, but maybe using these collectivity, I can basically enhance the interaction effects. So the idea then is that, can we do collective mode engineering? So use these collective effects in order to enhance the response. And this was the idea we came up with a couple of years ago now, which was basically if you just if you put your atoms in the right place, then you can basically massively enhance the optical depth. So if you make a sub-wavelength spaced monolayer of atoms, so this is a small cloud of about 20 atoms with a spacing of 0.9, then you get almost perfect reflectivity. So you get about 96% from about 20 atoms. So it works really well. And as you extend this lattice here to larger, you get higher and higher reflectivity. So that's a way that you can get very high optical depth. So I want to explain how that works first, and then we'll look at what happens in our current experiment. So to understand how that works, then, we need to understand this wave interference that Derek highlighted. So basically, if you think of light coming in, this is a focused Gaussian beam intensity pattern. Then I have some sort of pattern of intensity like this, so electric field squared. And if I look at the dipolar radiation pattern, it looks kind of similar. So this is just a vertically polarized dipole that emits everywhere. And then just in this particular plane, I look at the sum. And it turns out they're out of phase in the forward direction, but in phase in the backward direction. So I get destructive interference here and constructive interference in the backward direction. So my single dipole, if I focus strongly on it, looks like a very good mirror. So I get very good reflection from single dipoles. And basically, how good depends on how good I can do this mode matching. So that's one thing that we've heard about in various talks, is like people trying to mode match their field onto the dipolar field in order to get good extinction in the forward direction and hence high reflectivity. And I'm just going to advertise something I've also been doing, which is these pictures are from a book which is called Optics F2F, from Fourier to Fresnel. And you can now pre-order it on Amazon in time for Christmas. So that's advert over. OK, so what do we also know about single dipole? So it's very much in the green zone. And these were the pictures I showed at the beginning where I pointed out that line width is equal to decay rate. So everything is well behaved. Now, it's not until I introduce, say, a second dipole that I start to see something different happening, and I go into this collective regime. As soon as I have two, I'm basically collective. So here's the single dipole extinction. Now, if I bring in a second dipole, basically, life just gets worse, actually, pretty much. That basically, you destroy this nice mode matching that you've arranged, and now you see the mode matching is very poor, and often the extinction just goes down if I just add a second dipole. Because naively, when we started in this field, we thought, I just need to add more atoms, but adding more atoms doesn't always help. So you don't necessarily always do better. You need to be more intelligent about where you put your extra atom. And that's the idea of doing this, that basically you arrange your atoms in particular sites, and then you can get this very high extinction, because now you've basically arranged the system so that there are only various scattering states or modes that you can couple into. And as we saw in Derek's case, that by going to the sub-wavelength spacing, you basically create these scattered states outside the light cone. So if you like, I can no longer diffract transversely because the atom spacing is less than a wavelength. So I only have evanescent fields propagating in these perpendicular directions. So now I can only propagate forwards or backwards, and that gives me this almost perfect extinction. Now, because I can't no longer scatter out of the plane here, that's why the state is subradiant. So it no longer can couple to all the 4 pi of modes in the vacuum, and I can only couple to these forward and backward modes. So for this particular case, where I have a focused laser beam on about 20 atoms, the line width is about 0.4 of the usual spontaneous decay rate. And so this lower decay rate is a characteristic of subradiance. So this is an example of how you're exploiting these subradiant states in order to get enhanced light-matter coupling, which is something that is useful for all of us in terms of. So that's the basic idea. And you can sort of relate this monolayer physics. This is something that we're seeing more and more of. So these are very different but sort of related systems. So something we're studying in collaboration with Antoine Barre's group in Paris is these nano layers, where you have very thin layers of thermal atoms. And also there's a connection with this sort of emerging field of these transition metal dichalcinoids, which are these monolayers, a bit like graphene. But again, it seems to see that you see this collective enhancement of the reflectivity of these systems, which makes them very interesting. And these also have the possibility of doing Rydberg states similar to the cuprous oxide, which is an exciting direction that's currently emerging. OK, so we want to engineer these light-matter interactions to do something useful. But it's quite hard to arrange your atom in a sub-wavelength array. Lots of people do very nice experiments on this, but it's not currently what we have. So let's just look at the kind of collective effects that we might have if we just take a random ensemble and focus light through. And now we can do the same thing before we looked at the dynamics of all of these subradiant modes. And if we look at this system now, we can think of this as a kind of ensemble of pairs. And basically, all these pairs have different decay rates. And some are subradiant and some are superradiant. So if I look at the system, if I just take pair states and I plot basically the decay rate as a function of their separation, when they're separated very far, then I just get gamma. And when they come closer and closer, I see a change in the decay rate, and it spirals out. So when they're very close together, so up here I've got a decay rate approaching 2 gamma. This is the superradiant mode, where the 2 dipoles are oscillating in phase. And if the 2 dipoles are oscillating out of phase, then I'm down here with a decay rate. So that's the subradiant state with a decay rate of about 0.2 or so. And now the length scale for being whether I'm close or far depends on the oscillator wavelength. So for example, if you've got oscillators in the microwave, like microwaves, these things in these superconducting qubits here, you can separate them very far and still see these superradiant modes. So basically, the important length scale is what is the frequency of the dipole. Okay, so what happens with a random ensemble? So that's what the pairs are sort of well behaved. If you look at all the modes, what you find is a range of decay rates, as we see here, and a range of different, so there's some shift in the frequencies. So there's dispersion in the mode frequencies as well. Okay, so to understand what might happen in the experiment, let's actually look at the experimental results now. And our experiment, as I said, is very simple. We just take a cloud of cold atoms that's prepared in an optical dipole trap, but then we turn that off and probe the atoms with a focused laser beam. And we just send through a resonant pulse and then measure the time dependence of the signal that comes out the other side. And we isolate a true level system using magnetic field and a particular polarization. So it's about as simple light matter interaction experiment as you can conceive of. And this is the kind of data that we see. So this is a trace of our measured pulse. So this is the sort of raw pulse with no atoms here that goes off scale, well, up to 1. And then the light that's transmitted, we see an initial transient, and then it settles down to some steady state. And this steady state determines the optical depth of our medium. So e to the minus OD is what we're measuring as the transmission here. And then we turn the light field off, and you see this kind of pulse. And this is known as a flash. So this is a characteristic. So this is kind of a characteristic flash. And so that's what the kind of thing we're interested in measuring the decay of our medium, is to measure the decay time of this flash. So that's what we're going to measure. And if we measure that, what we see is it's about nearly 5 gamma 0. So it's really fast. So this was a surprise because our medium isn't very dense. So is this just a simple sort of superradiance? And how does it compare to, if we test this, our hypothesis that line width equals decay rate, what we find is that the line width isn't many gamma, actually. It's nowhere near 5 gamma. It's just a little bit more than gamma. So that was the real surprise in our experiment. And so we did more systematic measurements as a function of density or optical depth. And what you see here is that although the line width stays roughly constant at gamma, the decay rate is going up. So we find in our system that line width is not equal to decay rate. Now what's even more surprising is if we calculate all the decay rates of all the modes in our system from these coupled oscillator modes or these pair states, we find that we shouldn't really see any decay rates bigger than about 2. So the fastest superradiant mode has only got a decay rate of 2 gamma, and yet we're seeing something approaching 5 gamma. So we're actually faster than superradiant. So you've got these subradiant modes, superradiant modes, and then what we see is something completely unexpected. So we thought, oh gosh, there must be some problem with our experiment. But then we got Rob Bettles to do our theory. He's a very good theorist. He's now coming here to Barcelona in a few months. So, and this is the theory of Rob. So this blue curve here and these red points are experimental data. So basically Rob's theory confirmed our experiment. So then we had to understand, why is it the case that we see some dynamics that's faster than superradiance and that we see that line width is not equal to decay rate? Okay, so to understand, so first looking at the theory of the dynamics, so this is what happens actually if we, in the theory, as we turn off the field, there's the flash on a log scale, and there's the decay, and if we measure decay rate in units of gamma, then this is what we see. So there's an initial transient that's much faster, so it's a few gamma, but much faster than any of these superradiant modes in our system. So indeed, the theory confirms what we've been measuring in the experiment. So how does it work? So this is the final thing that I need to tell you. Well, it all comes back to this dispersion in these mode frequencies. So we've seen that superradiance is involved with a change in the decay rate. But what we sort of missed until now is the fact that the frequencies are always also shifted. And this dispersion in the mode frequencies gives rise to interferences that give rise to a faster decay. So you can see this very nicely in a 2 system. So again, here you get a decay that's very close to gamma. But what you see is a beating. So now there's a beating between the superradiant, the 2 modes of the superradiant and subradiant mode, because they have different frequencies. And so you see this oscillation in the decay rate, basically. And so initially, you can see a decay rate that's much faster than any of the eigenmodes because there's this interference effect. All right, so that brings me pretty much to the end of the talk. So I'd like to basically tell you that everyone in all their light matter experiments always has a collective system, unless you only have one atom and one photon. Then it's always collective. So you should basically revert to this collective mindset, because if you think collectively, you might be able to do things that you didn't imagine possible. And you can start thinking about collective mode engineering. And I've given some examples of where this is important and how it can be used to enhance the optical depth. But then I'd like to also remind you that the field is very rich, and this is many body physics, and sometimes you see very unexpected things, like so line width no longer equal to decay rate. We see decays that are faster than superradiant. So I'll finish there. Thank you.